Hello and welcome to the video going over question 16. So this question really mostly people only had trouble on A. They were able to do B and C just fine. But again, we're confusing using bond enthalpies to calculate entropy. Not entropy. Enthalpy. Versus using heats of formation to calculate enthalpy. And the processes are different. So heat of formation, which this question isn't, is products minus reactants. Look up, they give you, and you look up and add the products, and you minus the reactants. When you're using bond enthalpies, which can also be called bond dissociation energy, the process is different. So I'm going to now, which is using the reaction and data below, calculate the value of the standard enthalpy change, delta H, for the reaction below. So one of the things that causes people to mess up is they miss a bond. So what I like to do when I'm doing these is cross out the bonds as I include them in the reactants. So I see that there are a lot of carbon and hydrogen bonds. So there's 1, 2, 3, 4, 5. CH bonds. And so 5 times H is 413. And then I need to see if there's another bond. Well, there's a 1 CN bond here. And 1 CN bond is 293. And then I have a carbon-carbon bond. And some of you missed the carbon-carbon bond when you did this. So the carbon-carbon bond, there's one of those. And it is 348. And the last two bonds that we have are these are NH bonds. There are 2 of those. So NH is 2 times the NH, which is 391. And hopefully you can button press correctly. When you put all these things into your calculator, you get 3,488 if you button press correctly. Now I'm going to do the products. Same thing for the products. So if we go back up to the products, I see 1 carbon double bond, so right here. So carbon double bond, and that is 614. In terms of carbon-hydrogen bonds, I see 4 of those. So carbon-hydrogen, so this is times 1. So 4 times the carbon-hydrogen bond, which is 413. And so I've crossed off everything here, and then I have 3 NH bonds. So 3 times 391 from here. And then if I button press correctly, which I previously did this, and the phone is ringing, we get 3439. So I even get interruptions, it seems, while making videos. So now I added up but let's go back, because this is the important part and the part that you guys are missing. Or the concept that you guys are missing. So I added up all the bond enthalpies of the reactants, and I added up all the bond enthalpies of the products. Now, when you're in the reactants, you're breaking bonds. And when you're making products, you're forming bonds. So what you do, and I'm going to get a pretty colored pen out here, is that because the reactants stay positive, whatever you got for the products becomes negative, and then you simply add them together. And then when I added them together, I got delta H is equal to negative 49 kilojoules per mole. Okay, but this is not products minus reactants. It's you add up all the reactants, add up all the bonds in the products, and make the products negative because energy is released. So here energy is released, so we make them negative, and here energy is absorbed, so we make them positive. Now notice in an exothermic reaction, the bond enthalpies of the products are larger than the bond enthalpies of the reactants. So I'll say that again. Notice in an exothermic reaction, exothermic because this is negative. The bond enthalpies or the bond dissociation energy, either or, those words are used interchangeably, is greater than the bond dissociation energy or bond enthalpy of the reactants in an endothermic reaction. So B and C I'll do really quickly because we all got B and C, right? So if you got a reverse of the sign, you got B and C right based on your answer to delta H. So since the delta H is negative, the temperature of the environment should increase. That's because the reaction is exothermic and heat is released into the environment. As I'm slowly writing. And then we draw an energy, and all of you got this right. I mean, you could look it up because it was open book. But we have an axis, and none of you labeled the axes, but I didn't take up points. But when you're labeling the axes of an energy diagram, you put progress of the reaction on the x-axis, and usually potential energy on the y-axis. And since it's an exothermic reaction, the reactants should have more energy than the products because heat was released. Alright, so this is the video for question 16.